All right, so how do you show that GE is half of GH? Well, you know that FG and GH are equal, don't you? You have the bisector of the parallelogram, and then you have its diagonal, so it has to cross in the middle. So if you could, for example, show that these two were equal, or this EF was half of GH, you would have that. Or you can even show that just EF is a quarter of FH. Any of those things would be enough, right? So now Burke says, all right, crank the reel forward here to 1637. We're going to use a little bit of analytic geometry. And we can put, remember, these are ordinates here. The assumed equation of the parabola is that. So this is x sub c. This is x sub f or x sub h or x sub e or x sub g, whatever you like. It's the same one, right? And this one is x sub b or x sub q. And this is 0. All right. That's it. All right. So he goes ahead and calculates FE by analytic geometry. That would be the ordinate, the y-coordinate of E minus the y-coordinate of F. How would you calculate that? Well, the y-coordinate on the parabola is easy. That would just be A times x sub F squared, right? That would be, that's an E. What is it at F? This is the one that's a little obscure in the book. Yeah, the line doesn't go to the origin. Well, no problem. Look, go to xc squared multiplied by a. That gets you to here. That's the y of c. Now, he cranks forward a little bit further, gets a little piece of calculus there. The derivative is 2ax sub c. There, that's the slope of the dotted line that goes from c to f to q, right? That's the slope. So if you multiply that slope by this distance, you would get the rise. Add that to the ordinate of c, and you would get the total rise. Okay? Take that away from the one we just got for E. You have y sub e minus y sub f. That's the length of EF. All right. So what's this distance? This minus this is xf minus xc. Multiply that by twice a times xc. Well, that's the little hidden derivative in there, right? And add axc squared. That gives you the ordinate, the y sub f. Already have the y sub e. Take the difference. Rather than write, well, I have actually no place to write that out of. Keep looking at the. Balance through. No, sorry. Can't have everything. All right. Can you see any of this stuff here? It's just too far away. All right. It was kind of an involved little expression. So FE, this is the A times X sub F squared. Well, here's the great trick. X sub F is x sub c plus x sub b, remember b's up there, over 2. The average of them. So I put x plus b plus x plus c over 2. That is x sub f squared. That gives me y sub e. Now I take away y sub f. There it is. That's the ordinate at c. This is the derivative evaluated at c. And then this is the difference. XB minus XC is all of this. So I take half. There it is, half of XB minus XC. So I've restated everything in terms of XB and XC. B, C, 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 B, C. Right? So you have to get that out of the way or things become very obscure. All right, you simplified that algebraically, and you just crank through it. There's nothing great. And you get, at the end of the line, A over 4 times XB minus XC, the quantity squared. That's just what it is. That's the length of the little segment FE. Okay? You just hang in there with the algebra. That's what you get. On the other hand, BQ. Is it obvious that PC, HF, and BQ all have the same length? Okay? So if I'm trying to show that FE is a quarter of this, it'd be okay to show that it's a quarter of that as well, right? So let's see how long BQ is. It would be, BQ would be the difference between the wide B, the wide Q. So I go through the same thing. I evaluate, remember I'm assuming this parabolic equation. So AX sub B squared is YB. And the rest of this, that's the slope again of the tangent, right? And I add where I started from at C. So I get this, somewhat simpler expression. But this is exactly 4 times this one, right? So we have found that eventually FE is 1/4 of QB. QB and FH are the same, so it's 1/4 of FH. If this is a quarter of this, and this is a half, then these two little guys are equal, right? So this is at the bottom, quarter point, half point, end point. That's now been established. But that's enough by that earlier argument there to say that this triangle has a quarter of the area of this one. So that establishes the iteration step, the recursion step. And then the other argument has to do with the geometric series. That's the infinitary argument. Which I guess, from just glancing at what you showed me there, your book too said Archimedes wasn't real keen on it, but he suspected it was true, but he didn't have a justification for it. But like all great mathematicians, his intuition turned out to be right. Anyway, I'll give this to you so you have the thing. I hate to leave these things sort of poorly explained loose ends. And the book didn't do a great job with that. It was kind of a pro forma demonstration. Now, Phil's book here apparently has a synthetic proof of it. Oh, this is some ancient thing he got. It's a Britannica Great Books series.
Britannica has a series called Great Books that cover all kinds of authors, including Archimedes. One of the original papers.
Papyrus. Sand drawing, like kids do the sand castles. Okay, let's ratchet forward in time a little bit. I'll show you something that's not in the book.